Hello everybody, I'd like to thank you for your attention while we introduce ECHO 2, a post-release tracking device for small mammalian species. This project has been sponsored by SANCTUARI. This project was overseen and supported by Joe Morera, the founder of SANCTUARI, and Chris Rothwell, an industry-seasoned engineer who graduated from URI in the class of '81. We would like to thank these two for the endless support and guidance they've given us throughout the project. Our design team consists of 3 electrical engineering majors, Barry Huang, Ismail Mohammed, and myself, as well as Amani Hamid, our computer engineer. The goal for our team was to design a lightweight and non-obtrusive device that would be easily available for wildlife rehabilitators to maintain contact with and monitor small animals after they are released. SANCTUARI is a 501c3 nonprofit animal welfare, animal rights, and environmental organization. One of their main goals is to relieve wildlife rescuers with their financial, technical, and logistical burdens, which is where EM2 fits in helping. As a charity organization, the goals of SANCTUARI align much more with positive animal welfare outcomes than profit motives. However, technologies such as this one are designed to improve economic availability of tracking devices to rehabilitators as well as fill the market gap for affordable small tracking animal devices. The anticipated best outcome of our project include the long-lasting battery, size optimization, accurate data collection, and app configurability of the device. In the extent of our design time, we were able to use 2 integrated circuits to accurately collect GPS data and upload it to a database hosted on the cloud. Consumer-available development kits for these devices that we modified to be used together have been housed in a custom housing for testing. Additionally, we have designed and began testing for an all-encompassing printed circuit board for the project. Notable progress on this project made by the team that mark stepping stones in our development of meeting SANCTUARI's needs are listed here, notably the collection and reading of location data. Here's a system-level diagram of the project that you will see multiple times throughout this entire presentation. As outlined, the device uses a microcontroller called the BG24 to communicate with a multitude of sensors to send data to a database that is accessible through a mobile phone application. As mentioned, my name is Jack Russo, and to be more specific in my personal accomplishments, I would like to speak on my own work this year. I have been incredibly focused on and primarily responsible for the designing of a firmware application on our microcontroller that enabled it to periodically turn on the cellular chipset, collect GPS data, and post it to our database. Additionally, I was able to contribute by routing integral PCB sections as well as ordering the board and dealing with the fabrication company. During the ends of our design period, I developed a Flutter application for viewing the GPS data as well. The firmware app that is running on the BG24 microcontroller's functionality is outlined here. In the figure, the microcontroller PCB board is pictured in the bottom right of the image. I was able to lend myself to designing the schematic for our custom PCB. Some example circuitry that was designed by me include the accelerometer, the switches for turning on and off power to peripheral components, and the RF and wireless components like the antenna or the crystal oscillator. Here you can see the 3 tabs of the Flutter application as well as the root structure of our database. The first screen allows for configurable ping and post period as well as device connection. The second tab displays all the coordinates along with the date and time for the connected device. Lastly, the device uses the Google Maps API to display the points logged by the device on a neat map with direction indicated.
Hello, my name is Barry Huang. I am the second designer of this project. Here is the plot diagram again, just to remind you of how this project works. For my technical contributions in this project, I led the development of the first version of our PCB. I performed multiple schematic and layout corrections to address key design issues and improve functionality. I also led the design review for both the initial and revised versions, making sure our team stayed aligned and caught issues early. Beyond the PCB itself, I created a housing for our development kit to ensure easy transportation of the devices and all the components are securely mounted and accessible. Lastly, I performed a simple testing on the PCB and developed a document regarding improvements, component changes, and process of how to test. This is a block diagram that outlines the key components of our PCB design and shows how they are interconnected to achieve the system's overall functionality. On the left, the BG77 handles the GPS data, and the BG24 microcontroller serves as the brain of the system. It processes data, manages signals, and coordinates all the overall operations of the connected components. The power isolation block ensures efficient power usage by disconnecting unused circuitry. Our project has two PCBs. The main PCB is the tracking system. The second PCB is a theoretical design shown in Circuit Maker. It is a compact 1-inch by 1-inch board that houses the temperature sensor and the microphone. As you can see, the microphones are located at U1 and U3, and the temperature sensor is at U4, which is in the center of the board. It includes a 7-pin connector to receive power and signals from the main board. The main tools that we used for our project is Saturn PCB. Saturn PCB is an application that helps you calculate impedance matching and differential pairs. With the assistance of Mike Smith, I was able to correctly implement impedance and differential pair control for our signals, mainly for the Bluetooth antennas and the actual antenna itself. I used Saturn PCB tool to calculate the correct trace width and spacing based on our board stack-up and design constraints. Here's our main board that has been developed and tested through PCBWay. Despite even being tested through PCBWay, the very first thing I did when the PCB arrived was conduct a visual inspection to check the components that might have been damaged during soldering or transportation. I then used a multimeter to check for shorts between power and ground and to measure key components values to ensure they matched the design specifications. With the help of Jack, I was able to configure the pin multiplexing on the board and load a demo project for initialization. We confirmed the board was functioning by running a simple hello world print statement to the BG24 microcontroller, verifying it could successfully boot and communicate.
Hello, I'm Amani Hamid, the third designer of ELECOMP 2. Once again, this is the block diagram for the project. On the left, there is a Flutter application for smartphones, which is the one that I developed for this project. In this project, I built a Bluetooth-enabled trap system that communicates with a Flutter-based mobile app. The goal is to allow users to configure, control, and retrieve sensor data for a tracker device powered by BG24 chip. We are using Flutter for cross-platform development and Flutter Blue Plus for managing BLE communication. Currently, our work focuses on ensuring reliable task execution and data handling between the app and the device. I also focus on how the user configures and interacts with the app. I created a clear data structures for setting and control actions, such as starting or stopping a task. The data is formatted and sent to the device in a consistent way. This part ensures the app accurately defines how and when the trap collects sensor data. A major part of the work involved cleaning and organizing the BLE class to handle Bluetooth operations effectively. I added methods to connect, discover services, and manage MTU settings using retry logic to ensure we can recover from failed read or write attempts. This makes the communication between the app and the device more reliable, even when there are signal issues or delays. In addition to Bluetooth and sensor data, I worked on integrating Firebase into the app. I set up user authentication using Firebase Auth, connected Fire Store to store configuration and task data. I also use Firebase storage for handling large data files when needed. On the front end, I embedded Google Maps into the app, allowing us to display trap positions based on their GPS coordinates. This provides a visual and interactive way for users to manage and mentor their traps.
Hello, my name is Ismail Mohammed. I am the fourth designer of this project. Again, here's our state level block diagram. You can take a quick look just to review how it works. My technical contributions for this semester was creating a JSON document, doing Bluetooth configuration, and enhancing and correcting code via Simplicity Studio. This is the JSON document. This acted as a command structure used by the BG24 to control the BG77 module. It defines like simple readable instructions like starting GPS, switching to cellular mode, GPS timeout, upload interval, and so on. By using JSON, we keep the communication between the two modules flexible and human readable, which makes it easy to change it in the future or debug issues we might run into. Yep, that's it. For the Bluetooth configuration, I created a unique UUID in Simplicity Studio to set up Bluetooth communication with the BG24. I then designed a custom JSON-based protocol that lets other devices send configuration and control commands over Bluetooth. So this allows phones or computers to connect wirelessly to the BG24 and send commands in the form of JSON documents such as start GPS or upload data. And so if you connect to the certain characteristic and send a JSON document with a command start, then I'll start gathering GPS data and uploading it to the cloud. Okay, so after Jack and I finished our individual portions of the firmware, I combined our code into a single working system. Before this point, I was only simulating the JSON commands, but now once integrated, those commands are actually triggering hardware actions like powering on the GPS and switching modes. I also cleaned up the JSON document by removing parameters that were being used and ultimately unnecessary, such as battery mode, cell switch time, and GPS power mode. And then on top of that, I added error handling logic to catch failed responses or bad inputs so the system could recover gracefully and give us better debug info during testing. I added the error handling not just to the JSON document portion, but I also added it to the direct firmware that was sending the AT commands to the BG77.
We would like to thank those who have helped us thus far on this project. Program Director Dr. Hui Sunak, our Technical Director Joe Morera, our second Technical Director Chris Rothwell, and a special thanks to Professor Mike Smith for his assistance in our development of the PCB.